Good afternoon, ladies and gentlemen. My name is Rance. I am a PhD student in biological engineering at the University of Idaho in the Idaho Falls campus. Today, I am doing a literature review as part of my midterm exam for a structured class that is administered by Dr. Ian McCooey. The title of what we're doing is Removal of Nitrogen and Phosphorus from Polluted Surface Waters. A little bit of a background on myself. I am a registered professional engineer. I hold a master's degree in civil and environmental engineering from Utah State University. I have 25 years experience in civil engineering and environmental engineering consulting engineering. And I have 15 years experience in heavy civil construction. I have come back to school to get hopefully a PhD sometime in the next couple of years. And I'm doing this strictly as a learning experience. And that is what I am obtaining at this time. Again, I am a master's student, and I'd like to give you this presentation regarding the beginning of our research work. Eutrophication of surface waters is a major problem worldwide. It's not only here in the United States, but in many parts of the world, a very significant problem. The chief trigger for which is an overabundance of nitrogen and phosphorus, which is being added to our surface waters of lakes and streams by runoff of the storm waters and at direct addition via dead and decaying plant life and direct addition by animals, fisheries, and other sources. There are significant numbers of studies that are currently being done around the world and undertaken to try to develop a method and/or methods to remove and/or reduce the amounts of nitrogen and phosphorus that are being added in many different forms. This review that I have done represents a number of recent publications regarding the current researchers utilizing many different methods and a highly varying results. The publications that I have looked at this point are in the last 5 years, and they are the ones that we will be looking at this afternoon. Part of what we have, I just give you a little quickie here, is RPA, I will be using that term, is a researched published article. Our first RPA is entitled A Study of the Experimental Performance of a Bio-ecological Floating Bed for Nitrogen and Phosphorus Removal in Eutrophic Water. This is a Chinese study, and it's using 34 different types of algae, which they call bacterial growth, to remove nutrients. They had also, to improve the efficiency, they use sacrificial anodes of iron and aluminum to improve the removal rates through enhanced coagulation. Their study period ranged from 14 to 18 days per type, half of which were tested under anaerobic conditions and the other half under aerobic conditions. The best removal rate that they found for nitrogen was 58% at 15 days and or 70% at 18 days for phosphorus. A biochar substrate was added to the samples to enhance their biological growth and increase removal performance. It's interesting, however, to note that they did not identify the type or the amount of the biochar substrate that was added. It seems to me like this was a fairly important item that was not presented. Our next RPA is entitled Phosphorus Removal from Aquaculture Effluents at the North Fisheries Center in Lamar, Pennsylvania, using iron oxide sorption media. This report and this research involved 3 different sorption medias, 2 of which were acid mine drainages waters, and 1 was granular ferric oxide. I have to assume the mine drainages were coal mines, since that is a big deal in the Pennsylvania region. Nitrogen removal that they observed ranged from 50 to 55%, over a 223-day study period without regeneration of any of the oxides. The phosphorus removal was 50 to 70% over 70 to 175-day study period, also without regeneration. Regeneration here, obviously these absorption medias were flowing from and through the facility, and it allowed them to have these long study days. Our next RPA is entitled Phosphorus Removal Option for Hatchery Wastewater Effluents. A little history here. Aquaculture is the fastest food growing source in the world. In 1991, production was only 18 million tons, but in 2006, 66.7 million tons were produced in aquaculture. Aquaculture being captive rearing. Another little tidbit here is in the United States, 75% of all rainbow trout that were grown under aquaculture conditions were grown in Idaho. And the majority of that was in Hagerman under the tutelage of the Thousand Springs exit of the Snake River Plain. Effluent P from hatchery is a fairly low phosphorus reading, but it is very high in volume due to the fact that you have to continuously keep flowing water moving at all times. 20 to 30% of available nitrogen fish and phosphorus in the fish food is utilized by the fish. The remaining part is either lost in the feeding process and or through the excrement process. The options here in this particular study used a constructed wetlands followed by filter beds to treat the effluent coming from the hatchery. They used over 80 different types of materials for filters, most which are naturally occurring filters, such as shale, fly ash, limestone, sand and gravel, steel slag, asbestos fibers, and a number of others, obviously, to get to the high number. Removals were highly variable. At best, though, they only represented 50 to 60% of the available. The next RPA that we're talking about will be reactive nitrogen and phosphorus removal from aquatic effluents utilizing polymetric hydrogels. The hydrogels that they were using on this were specifically formulated to chemically bond with various forms of nitrogen and phosphorus, of which there were a high number. The hydrogels were capable of being washed for reuse with utilizing ammonia hydroxide. One thing they did find, however, that the washing was not complete because removal capacities decreased as they washed them for reuse. Removals resulted to approximately 10 milligrams per liter for nitrogen in various forms and 0.3 milligrams per liter for phosphorus in numerous forms. Should be noted, though, that even though this forms are removed to these levels, the 0.3 milligrams per liter for phosphorus does not meet the Idaho standards for clean water. Suspended solids in this case had a major effect on removal rates. The best removal rates required screening of the effluent to remove suspended solids. My question here in this respect was, how about settling solids? Did they use any settling to achieve these results? And they did not address that. The next RPA is entitled Total Nitrogen and Total Phosphorus Removal from Brackish Aquaculture Wastewater Using Effective Microorganisms. The effluent that they used in this study was from a sea bass facility. The effective dosage of the effective microorganisms was at a ratio of 1 to 1,666. Seems to me like that's a very small contribution for the large number that were there. That's not seemingly balanced very well. The pH was adjusted to 7.0. Removal was 81.5% for nitrogen and 38.9% for phosphorus. That also seems to be very low, and with as far as our removal, but again, we're starting hopefully with a fairly small rate. Extending their treatment time to 6 days modified removals to 99.78% for nitrogen and 62.8% for phosphorus. Here again, we're looking at percentages that are not necessarily compatible with the approval rates. Our next RPA is entitled Simultaneous Ammonia, Nitrogen, and Phosphorus Removal from Micropolluted Water by Biological Aeration Filters with Different Media. A statement that they had to begin with said lightly polluted waters are hard to treat by conventional means. That is something that is absolutely true. Through my history, I haven't found that to be totally true. The study utilized 3 different medias as they're raising their biological filters, including volcanic rock, ceramsite, and zeolite. Media added was a 1-to-1 ratio by volume. This also seems to be a very high ratio to add media. Detention time and the treatment was 3 hours, and the best P reduction was on the volcanic rock, which had 67.4% phosphorus reduction. Back to the 1-by-1 ratio by volume, obviously volcanic rock showing up very well and being very plentiful in Idaho. This is, but it sounds like a terrible ratio to have to handle to get the treatment. Our next RPA is entitled Discharge Management in Fresh and Brackish Waters, RAS, Combined Phosphorus by Organic Flocculants and Nitrogen Removal in Wood Chip Reactor. They utilized in this research a recirculation biochip reactor, to which they added carbon absorption chemicals, both anionic and cationic, of which they were constructed from potato starch. Again, a very interesting item for being in Idaho and being the potato capital of the world. This absorption chemical, potato starch, created a very strong absorption flock. They operated the test for 6 weeks, found the phosphorus removal from fresh water was 56%, and the phosphorus removal from brackish water was only 49%. Obviously, the brackish water contained something that was adjusting the chemical or the phosphorus organics and was actually destroying them. Nitrogen removal was variable and dependent upon the P removal rate, and it needs to be further worked to be commercially viable. The nitrogen, obviously, in the organics was dependent upon the phosphorus for providing the great strain and the ability to multiply. Our next RPA is entitled Study on the Experimental Performance by Electrolysis Integrated Ecological Floating Bed for Nitrogen and Phosphorus Removal in Eutrophic Waters. Removal rates in this study were measured by analyzing plant growth of the floating bed. I'm not sure exactly how they did that, other than as they found that they were doing this by individuals, plants. P removal was measured to be up to 76.5%. Substrate additions were made to check for adding efficiencies. The additions of the substrates that they were using included zeolite, sponge iron, rice straw, plastic filings, and ceramides. The substrate removal with substrate found to produce the phosphorus removal was actually reduced to 74.5%. The substrates obviously had a deleterious effect on the floating bed, and it reduced the ability to treatment. So they actually killed or destroyed some of the substrates. Our next RPA, removal of nitrogen and phosphorus pollutants from water by ferric chloride impregnated biochar. This is a very interesting sermon to me, because the biochar is something I am going to be looking at in my master's work, or my doctorate's work, excuse me. The layer of 1% ferric oxide was added to the biochar, and it had a 10% impregnation into the biochar. The study used an agricultural runoff with an 85% P removal. The P bond in the biochar was very high, as only 5% or 1/2% was released upon resorption. The material charred was not identified, which I thought they should have done. The strong bond was not advantageous so that the biochar could be reused as a fertilizer. And they noted that they felt like a potential significant added cost would be recognized with the ferric chloride. The next RPA is a newly established free water service constructed wetlands to treat agricultural waters in the low-lying Venetian plain. Performance on nitrogen and phosphorus removal. This particular research was done in Italy with the Venetian plain and had a 5-cell newly constructed treatment unit on approximately an 80 hectare farm. The 5 cells had a total surface area of 2 hectares with depths ranging from 0.4 meters, which they called a shallow pond, to 0.6 meters, which was identified as a deep pond. The shallow pond had a different type of plant life than the deep pond. And that was, they did this by design. The hydraulic detention time was 8 to 10 days under normal conditions. The nitrogen and phosphorus removal rates were highly variable, depending upon the time of the year, the water pH, the air temperature, the rate of contributing flow and turbidity of contributing flow, which in turn helped or affected the detention time. Sometimes it was much less, sometimes it was longer than the 8 to 10 normal. No discussion on plant harvesting, just the opposite. Some added nutrients were reported with plant decay and algal decay as represented by their test results. The next RPA is determined the efficiency of nitrogen and phosphorus removal by 6 microphytes from eutrophic waters. 6 different plant species were used in this study that took 28 days, and the removal by plant uptake in the growth cycles is what was being measured. 3 concentration levels were tested for both nitrogen and phosphorus, as these were introduced in by the eutrophic water. They were called low, high, and very high. The results from each of these was tested in the 14, 21, and 28 days. And as you might expect, the results were highly variable. Some removals were better at 14 days than at 28 days. This means that some of those plants had exceeded their excessive growth time in the 14 days rather than 28. Key to efficiency was the harvesting of plants at least 3 times per growing season. The harvested plants were projected to be used as fertilizer with the nitrogen and phosphorus that they had uptaken to be used as the fertilizer and use release. Removal rates were phosphorus dependent. That was their growth weight for nitrogen removal. Nitrogen removal varied from 20 to 85%, depending upon the time, the variety, and the P level that actually controlled the growth. Phosphorus removal varied from 65 to 95%, depending upon their initial concentration of the plant, the type, and the plant variety. Here again, we're talking about percent. I don't know what the real numbers were that we're left with. The next RPA is called Advanced Treatment of Salty Eutrophication Water using Algal Bacteria Granular Sludge with a focus on nitrogen removal, phosphorus removal, and lipid accumulation. This study utilized both a 2% and a 4% salinity water. The growing period for the algae on the sludge was 15 days before they began their function. Inorganic nitrogen removal was 2% in 98 days and in 4% reduced to 17%. That means, of course, that the antibacterial growth had suffered severe damage at that time, under 4%. Phosphorus removal was 2%, was also 98%, and 4% phosphorus actually increased, which means, again, the decaying and the dying antibacterial units on the sludge were adding back into the waters. Strong algal growth in 2% water aided the high removal rate, obviously, but there was light to no growth in 4%. In fact, there was actually decay to obtain the percentages that they were getting. The lipid production in 2% was good, but better in 4%. And it was noted that lipids have a strong potential for biodiesel production. Our next RPA is entitled Effects of a Combined Biological Restoration Technology on Nitrogen and Phosphorus Removal from Eutrophic Waters. This particular study was a very different study from anything else that we looked at. The study utilizes submerged macrophytes, filter feeding bivalves, and planktivorous fish, in this case, silver carp, to reduce the algal load. Experiments were performed in concrete tanks in September and October, which are not the ideal conditions for the growth of algae. Macrophytes showed good growth. The bivalves and fish were weight stable or some loss. This was demonstrated by the fact that they actually took the individual bivalves and fish and weighed them at the beginning and at the end of the study. The bivalves and fish were responsible actually for some increase in both nitrogen and phosphorus by stirring the sediment in the tanks and getting that material up into the water where they were sampled. Overall, they were rated as having a positive influence. However, the macrophytes were the major contributor to the removals. Removal was measured by weight of the 3 bioforms pre and post study. This sounds like an awful lot of work and not knowing exactly what was going on, and particularly with the bivalves and the fish. Conclusion, however, was that this study was a success. Again, I'm not sure what the definition of success was in this particular case. Our next RPA is entitled Influence of Natural Oxygenation of Baltic Proper Deep Water on Benthic Recycling and Removal of Phosphorus, Nitrogen, Silicon, and Carbon. This is a study conducted in 2014 when a major Baltic inflow from the Atlantic Ocean brought in oxygenated salty water into the Baltic Sea. The Baltic Sea is normally a brackish water with associated nutrients and flora compatible to that brackishness. That was changed drastically by the Baltic inflow. The intrusion caused a major upset in both the temperature and oxygen thermoclines in the Baltic Sea. This upset was capable of bringing in significant oxygen into the anatoxic and the benthic zones. Sediment, nitrogen, and P were both reduced due to the oxygenation of the benthic zone. And additionally, nitrogen and P were made available to sea plants and flora, which in turn converted that, but the stirring up of the sediments put a lot of material into the sea and allowed for the plants and flora to flourish and significantly affect the existing conditions. The next RPA we have is entitled Potential of Duckweed Luma minor for Removal of Nitrogen and Phosphorus from Water Under Salt Stress. Duckweed is a very rapidly growing water plant that has an excellent nitrogen uptake. And that has been seen in many, many places around the world where duckweed just simply overtakes the water course that it is found in. This study was a bench scale test using different levels of sodium chloride in the water of 0, 25, 50, 75, and 100 parts per million. That gets from some very nothing, obviously, to some very high nutrients in this test. The removal rates were good in the lower waters of 0 to 50 parts per million, but reduced at the upper levels. The duckweed was obviously not tolerated at the higher levels. It had slow accumulation and some mortality. Many different species of duckweed are available. Each has a very different tolerance for salt water, and they warn to be careful and cautious of which you use. Sometimes I think you're not going to have a choice, but you have to be careful on how you handle it. Our next RPA is called removal of nitrogen and phosphorus from floating degraded river and wetland water using sphagnum floating bed. Sphagnum is a member of the moss family and has a high affinity for carbon assimilation and utilizes nitrogen and phosphorus in proportion to its assimilation of carbon and in proportion to its growth. Sphagnum reacts very well to fluctuating water levels, including dry periods, which makes it very handy in some places where you have high water through initial rain, and then you go for periods of time in drought. Sphagnum reacts well to high nitrogen and low phosphorus, as well as low nitrogen and high phosphorus. In other words, it's not dependent on one or the other for its growth potential. In field evaluation over a 3-month period showed a significant increase in the content of both nitrogen and phosphorus in the moss. To recognize the uptake and its benefit to the environment, harvesting of the moss will be required, and they recommend the best time would be in October. That again gets you out of the normal growth period. The next RPA we look at is characteristics of nitrogen and phosphorus removal by a surface flow constructed wetland for polluted river water treatment. This was a 2-year study of a newly constructed wetland utilizing 2 local species of plants. In this case, it was a reed and a cattail. The wetland involved 900 square meters with a flow of 1,000 meters a day of municipal and ag effluents. Initial removal was very good and increased exponentially with the rapid growth and development of the 2 plant species. Continued high development was dependent upon plant harvesting. Conclusions were reached by individual plant harvesting and analysis. In this case, they had identified the specific location for each of the seed plants that were put into the wetlands, and then they harvested them and watched them as the seeds dispersed and grew, and then they weighed them and analyzed them for their input and uptake. Our next RPA is entitled Nitrogen and Phosphorus Removal from Contaminated Water by 5 Aquatic Plants. The 5 aquatic plants are all identified here, and I will not butcher them because I am not a botanist, and most of these I cannot pronounce. The study here was conducted at a bench test over a 60-day period. Removal rates were measured in conjunction with the growth rates of the individual species. Here again, they were measuring and weighing the individual plants. The wastewater was a prepared sample. Most efficient removal was by the A calamus with a 97.7% nitrogen and a 96.1% phosphorus. 3 others had a 90% plus removal of the nitrogen and a 75% plus removal of phosphorus. The S. signatifolia had the worst results at 43.6% nitrogen and 33.5% removal of the phosphorus. The top 4 plants were recommended for use in surface water treatment systems. Here again, we're finding that they're using 0.7%, 0.1%, and they were measured in the growth rate of the individual species. This seems to be a little bit of a take on efficiency for me. The next RPA is entitled a biological floating bed and biocontact oxidation process for landscape water treatment with simultaneous removal of microcysticrisia, TOC, nitrogen, and phosphorus. This was a bench scale study to determine the effectiveness of algacidal bacteria J25 in removing harmful algae from wastewater. I think it's interesting to note that this is looking at an algacidal bacteria and J25, something which no other work that I have seen was looking at is a whole different direction. 4 strains of algae were evaluated, and the study period was 32 days. In this case, they used a parallel test reactors to confirm their results. The best nitrogen removal was 88.83%. Best phosphorus removal was 33.07%. Algal cell removal was 53.43% and varied with the species that they were evaluating. Here again, carrying out these removal rates to the 100th of a percent makes me wonder exactly what's going on, because I don't see this as being practical. 53% would be just fine. Our next RPA is entitled The Growth Traits of Microalgae for Biofuel and its Effect on Nitrogen and Phosphorus Removal in Wastewater. This is a Chinese study, and China is rich in coal, but shy in oil and gas reserves. Many researchers in China are working on developing a biodiesel fuel source. This research was carried out as a bench scale project to evaluate the potential of 4 microalgae species to provide such a source for biodiesel. 2 of the species were obtained in the United States and 2 were native Chinese. Initial algal growth for the 4 species was similar for the first 13 days, and it was possible production of oil might be similar. Best nitrogen removal and P removal was 48.2% and 97.8% for chlorella, which was a US strain. Again, we're talking about getting down into the nitty-gritty of the percentages. I don't understand. Observations and conclusions that I had in this review. There are many researchers around the world who are looking for a method or methods to remove nutrients from our water supply system and therefore reduce the eutrophication effects that they impose. The majority of the current published papers are supported by Chinese learning institutions. They probably 75% of the papers that we have reviewed today were supplied and were backed by Chinese learning institutions. There does not seem to be any common thread between the research work that's being done, the results that are being got, and there is a wide approach being tried to solve the problem. Obviously, in basic research, you try a lot of things around, and that's what is evidently we're at. We're really in the basic research, trying anything and everything. To date, no golden goose has been identified. Obviously, the golden goose is the one that will do the job, but that hasn't been identified at this point. Some common omissions that I see among the majority of the papers include the following. Research involving plant growth, of which there were a number of papers, has included statements requiring harvesting of the plants, but they did not address the methodology, the costs, and how the plants were to be disposable, whether they were capable of being used as fertilizer, they may be toxic at fertilizer, or some other methodology that might have to be used. Most articles did not offer any recommendations for follow-up work. I think this would have been a very important issue of how and what they have done, what they found, and what was the need for follow-up, and what might be the method of follow-up. There was hardly any method, any mention of economics of the methodology used in the research being reported. And again, understanding that we're looking at the basic areas and methodologies, the economics may not have been able to be defined precisely, but the scale of the economics should have been reported, I feel, to give some basic unit and give some measure of the effectiveness and the possibility. Removal rates, and I've mentioned this a couple of times, were reported in percentages rather than level. And the percentages carried out to the 100th%, to me, just did not make sense, but it was something that they reported, so I reported it. The United States standards are set by levels, such as 0.075 milligrams per liter, which is the Idaho standards for phosphorus in fresh water. And by reporting in percentages, I really have no way of knowing if their percentages are capable of meeting the standards that have been set. We need to have a continued and a current method of reporting so that they have a uniform and method and have uniform results and interpretations. That concludes my report. I thank you for attending. I hope that you will have a great day, and I hope this has provided some insight for you as the reviewer to see the scope and parts of what is being done. I'm sure in the future that there are going to be more reports that'll help us narrow the scope, and maybe the golden goose will be found. Thank you, and again, have a great day.